The next section we're going to cover is section 6.3, the definite integral and area under a graph. If f of x is a continuous, non-negative function on the interval from a to b, we refer to the area of the region shown in the figure as the area under the graph, often referred to as the area under a curve from a to b, or the area bounded by the graph of f of x, the x-axis, and the vertical lines x equals a and x equals b. Let's take, for example, what we think we would do to find the area under the curve of f of x equals 4 from x equals 0 to x equals 3. Well, we have to consider what is the graph of f of x equals 4. So that graph, well, you would have to have an x-axis. You would have to have a y-axis. And then it would also have to have this graph of f of x equals 4. Well, that's a horizontal line through y equal to 4, because remember this is y equals f of x. So here's our f of x axis, here's our x-axis. So our line here is y equals f of x, which is equal to 4. And then what we want to do is we want to look at it. I'm going to figure out what the area is between that curve and the x-axis from x equals 0 to x equals 3. Or the area in here. That's from x equals 0 to x equals 3. So what we have to remember is this is a rectangle. And usually when we're trying to find the area of a rectangle, we're looking at this area. And a rectangle has an area that is equal to length times width. Well, the length is from 0 to 3. That length is 3. And its width here, or height if you will, goes from y equals 0 to y equals 4. So its width is 4. So overall, that leads us to an area, which is length times width, of 4 times 3, which is 12 square units. And here I gave you a better picture than I can draw, and this is our solution, and it agrees with us. We have an area of this rectangle bounded between y equals 0 and y equals 4, going from x equals 0 to x equals 3. And the area was 12, which is 4 times 3. So once again, you had w equals 4 here, and L equals 3 here. So our area, which is length times width, was 4 times 3, or 3 times 4, which is 12 square units. If we look at g of x equals negative x plus 4, and we want to find its area between 2 and 3, we can break it down. We can break it down into a triangle and a rectangle. It's actually a square, but it's the way the scales have been drawn here, it makes it look more like a rectangle. So if we wanted to find that area, it says the area is 3 halves. So how would we find that? Well, we would look at the area of that square, which is, well, 2 to 3 has a width of 1, or a length of 1. And 0 to 1 here has a distance also of 1. So we've got a 1 by 1 square whose area then is 1 by 1, or 1 square unit. If we looked instead at the triangle, it still has the same length of 1 and a height also of 1. So the area of a triangle is equal to 1/2 base height. And in this case, our base is what I labeled as length. So it's 1/2 times 1 times 1, or 1/2. If we add these two together, we get 1 plus 1/2, which is 3/2 square units. If we looked at the example on the right, we're going to find that we can do something very, very similar. Because we can think of this as a square, where it is 2 units on this side, 2 units on this side. And it's also this triangle here that has a height of 2 units. Let me do that in a color you can actually see. Here, it has a height of 2, and it has a base of 2. So if we were to look at what this means in terms of area, our total area would be the area of the triangle, which is 1/2 base height, plus the area of the square, which is length times width. So what we find is our area is 1/2 times 2 times 2 plus 2 times 2. So in the end, we end up with 2 plus 4, or an area of 6 square units. And at this point, you're probably wondering why we're looking at areas of rectangles, areas of triangles. What is it we're trying to do? Well, that's what we're going to look at on the next slide. We have a theorem about the area under a curve, the area under a graph. If f of x is continuous and non-negative, and it's a function and it's defined from a to b, then the area under that graph of f of x between the graph and the x-axis from x equals a to x equals b is equal to the definite integral of the function from a to b. Let's look at an example of this. So we found the area of f of x equals 4 from x equals 0 to 3 to be 12 using length times width. Let's instead try it by doing theorem 1 about the area under a graph. So here we're told that our area is the definite integral from a to b of f of x dx. Well, in our case, that means our area is the integral from x equals 0 to x equals 3, and our f of x here is just 4. So the integral of 4 is 4x from x equals 0 to 3. So that means it's 4 times 3 minus 4 times 0, or our area is 12 square units. This agrees with what we found just looking at it as a rectangle. So what about the other two examples that we looked at? Let's see if they also come up with the same area based on the theorem of the area under a curve versus using the triangle and the square added together for each one. Let's start with the first one, where we had g of x is equal to negative x plus 4. And in this case, we want to find our area from 2, which is our A, to 3, which is our B. So our A is 2, our B is 3, and our function is negative x plus 4 dx. So we need to find the area under our curve by integrating negative x plus 4. Well, negative x came from a negative 1/2 x squared, and 4 came from a 4x, and we want to evaluate that new function from x equals 2 to x equals 3. So we end up with negative 1/2 times 3 squared plus 4 times 3 minus negative 1/2 times 2 squared plus 4 times 2. So if we start simplifying this, we find that we get an area that is, what, negative 9/2 plus 12. Let's see here, 4 divided by 2 is just 2, so minus this is negative 2 plus 8. So we end up with negative 9/2 plus 12 plus 2 and minus 8. If we add all of that up, we get, what, 12 plus 2 is 14, minus 8 is 6. 6 minus 9/2 is 12/2 minus 9/2. Indeed, then, we will end up with an area of 3/2 square units, which matches what we found when we looked at the triangle plus the square. Let's see if it holds for the last example. In this one, we have a special kind of function. This one, it has a function that we call a step function. A step function means it's equal to one thing for a certain value of x, and it's equal to something else for other values of x. So what we have to do is identify which one is which. So we know that if x is greater than 2, our function h of x is just equal to 2. That's this part up here, this horizontal part. However, if x is between 0 and 2, we have this slanted part, which is our h of x equals x. So in order to set up this area, we're going to have to set up two different integrals, because the area under the first part is going to be using a different function than the area under the second part. So what we're going to have to do is say that now our area, oops, let me get my pen a little smaller again. Okay, so our area here now is going to be the area from 0 to 2, where we only use h of x equal to 2x. So it's x from 0 to 2, or integral from 0 to 2 of x dx. And then we're going to add to it the integral from then 2 to 4. And at that point, our h of x changes to just 2 dx. So when we start evaluating, we find out here that the integral of x is 1/2 x squared, and that's going from 0 to 2. And then plus the integral of 2 is just 2x. And we'll evaluate that one from 2 to 4. We have to break it up into pieces because the function itself is broken up into pieces. So when we start to find that area, we know we get 1/2 times 2 squared minus 1/2 times 0 squared here. We're going to add to it 2 times 4 minus 2 times 2. Or we get an area of, let's see, 2 squared is 4, divided by 2 is 2, minus, well, that part's 0, plus 8 minus 4. So we get 10 minus 4, so our area is 6 square units, which matches exactly with what we found by adding up the triangle and the square. But what happens if we can't break up our pictures into triangles and squares and rectangles and things that we know how to find an area for? Luckily, we've just developed our skills at using Theorem 1 to help us out with that. So here's another example. Let's look at the area under this graph. This graph is f of x equals 3x squared plus e to the x. And we want to find the area under that curve from x equals -1 to x equals +1. So what we're going to do, and the problem is given to us there, but we're going to work it out ourselves. We're going to say that means our area is the definite integral from a is -1 to b is now +1 of our function, of our function 3x squared plus e to the x dx. And let's see if we get the same area as the one listed on the diagram. So 3x squared came from an x cubed, and e to the x, its integral is just e to the x. And let's evaluate it from -1 to 1. So we end up with 1 cubed plus e to the 1 minus -1 cubed plus e to the -1. Or 1 plus e minus a -1 plus e to the -1. Well, two negatives make a positive, so we end up with 2 plus e minus e to the -1. Or 2 plus e minus 1 over e. And remember, e is just a number, 2.718281828, and it goes on from there. If we were to plug that into our calculator, we would find that this equates to just about 4.35, which is exactly what the diagram tells us it should be. Let's try one more. I'd like for you to try this one on your own. You know the area is supposed to be 2.25. I would like for you to pause your video here and see if you can figure out how to set up your integral involving our function f of x equals x cubed plus 2x plus 1 from x equals 0 to x equals 1. And then I want you to come back and see if you got the same solution and in the same way. All right, let's see what we get when we do it together. So we have our area from a equals 0 to a equals 1 of our function, which is x cubed plus 2x plus 1 dx. So x cubed came from a 1/4 x to the 4th. 2x came from x squared, and 1 came from a 1x. And we're going to evaluate this function from 0 to 1. So that means our area then is 1/4 times 1 to the 4th plus 1 squared plus 1 minus, well, 0 plus 0 plus 0. Right? Every time we plug in a 0 for x, all of those terms become 0. So really what we get is 1/4 plus 1 plus 1, or 2.25. 0.25. So hopefully you were able to come up with the same answer and in the same way. If not, I want you to pause here, rewind it a little bit, and go through it one more time and try it one more time on your own, and then watch it again to see if you got the same answer. For this next example, we don't have a graph. We want to find the area under the curve y equals 3x squared from x equals -1 to x equals 1. So just in case, we might want to see what a graph of 3x squared looks like. Well, 3x squared is a quadratic. And this quadratic starts and stops and reflects around the origin. The vertex is at the origin. And what we're looking at is the area from -1 to 1. This area under here plus this area under here. Because both regions are still positive, we can do it in exactly the same way as we've done so far. So we know then that our area here is going to be the integral, the definite integral from -1 to 1 of 3x squared dx. Well, we also know that 3x squared came from an x cubed, and we're going to evaluate it from -1 to 1. Well, that would be 1 cubed minus -1 cubed, or 1 plus 1. Our area here would be 2 square units. Well, what happens when things get a little more complicated? Because now we have y equals the square root of x, and we want to find the area under the curve y equals the square root of x from x equals 0 to x equals 4. Well, if we graph y equals the square root of x, this is what it looks like. And we want to go from x equals 0 out to x equals 4. And we want to find this area under the graph. So how are we going to find that area? Well, it's always between the graph and the x-axis. It's always positive. So we're going to use theorem 1 again and say we're going to integrate from 0 to 4 of the square root of x dx. This is where remembering our rational exponents is going to get really handy, because we can convert the square root of x into x to the 1/2 dx. And when we do that, we can use our power rule from integration, where we say that that means this was 1 over the new power. Well, x to the 1/2 plus 1 gives us x to the 3/2. So we get 1 over 3/2, x to the 3/2 from 0 to 4. If we want to simplify that, 1 over 3/2 is the same as 1 times, and then remember our rules for fractions, you flip and multiply the second one, so it becomes 1 times 2/3. So we really get 2/3 x to the 3/2, which we want to evaluate from x equals 0 to x equals 4. So when we plug that in, we get 2/3 times 4 to the 3/2 minus 2/3 times 0 to the 3/2. That makes our area here 2/3 times 8 minus 0, or 16/3. If you want it as a decimal, it's approximately 5.333. So in this section, we learned how to find the area under a graph between that function and the x-axis. So what happens if that graph doesn't always stay above the x-axis? Well, we're going to cover that in the next video for section 6.4. For this section, 6.3, I want you to take some time, look over some example problems in the book if you'd like to try some more, and then please remember to do your Pearson online homework for section 6.3 and upload your daily notes for section 6.3 to our Blackboard site.